Just checking.
Okay, so last up this morning we've got Kate Fisher.
Thank you. Let me know if you can't hear me. I'll do what I can. But I'm going to be speaking on some of my work that's ongoing with my advisor, Yusuf Marzouk, where we're proposing an approach to evaluating the uncertainty descriptions given by Bayesian neural networks. So I think some of the talks given before, particularly by Jeremias and Arno yesterday, have set up some of the themes I'm interested in, and we'll revisit a few of these. What I really want to start with is the question of what if computational cost was off the table? What would the ideal approach of uncertainty quantifications for neural networks be if we didn't have to worry about doing approximations to make things practical? Of course, we are living in the real world, but we should have some intuition on the answer to this question so we know what exactly we want to be approximating. There are a lot of options out there already for uncertainty quantification for neural networks, so you can easily get some sort of set or some distribution, but there are certain interpretability difficulties for these methods because a lot of them are ad hoc or rely on approximation. We can also, of course, use things like conformal prediction, and given a correct data set, we can get validity guarantees, but this is model agnostic, as has been pointed out. We have the intuition from what we understand of neural networks that their generalization behavior is really impacted by the types of parameters they have, the number of parameters they have, the specific architecture they use. So we can have the intuition that maybe there should be an approach to uncertainty quantification that engages with these parameters. And really, we want to figure out whether Bayesian neural networks can be considered this approach, because as some people have pointed out, Bayesian methods can be sort of a default for uncertainty quantification. So I'll go over a little bit of how we expect Bayesian methods to work, specifically for neural networks, before getting into the model we propose using, which uses discrete priors in order to get a realistic representation specifically of the Bayesian predictive distribution. Then we'll try to figure out when exactly Bayesian neural networks are calibrated. To start with, here's the model class that we're interested in. We're going to be separating the last layer weights a bit from the interior weights, so we call the final layer weights W. The interior parameters that we're interested in are the theta parameters as well as the biases. And if we want to be Bayesian about learning these parameters, we can assign them some sort of prior, figure out a likelihood model for our data, and then proceed with Bayesian inference to get a posterior distribution on our parameters, and through marginalization, the posterior predictive distribution on our new data points that we might observe. There are a lot of reasons why people have the intuition that Bayesian methods are going to be a good approach for uncertainty quantification. First of all, you end up with an object that, at least on paper, has a clear mathematical interpretation. And you have these nice Bernstein-von Mises properties that tell you that you can concentrate to a reasonable point within your model class. Of course, this can be a bit of a sticking point in traditional applications of Bayesian methods because in many cases your truth is going to be outside of your model class, and you can quickly become confident in the wrong thing, as is shown by this fairly simple example where you simply don't have the correct model in your class and you are pretty sure about the wrong model with only a few data points. Using neural networks would seem to fix this problem. Even a single hidden layer neural network is a universal approximator for a sufficient size. So by using an extremely flexible model class, you might seem to fix the problem of model misspecification. So why do we still have some doubts about using Bayesian neural networks? First of all, we've gotten a bit away from the traditional idea of how to use Bayesian probability to represent beliefs about things that you can clearly describe. you end up with an extremely large model in terms of parameters, and you don't really know how exactly these parameters work together to represent certain physical processes in many cases. Further, based on what we do know of generalization, while it relies on architecture and optimization, there's also something special about the training algorithms that people use to learn neural networks, and that things like stochastic gradient descent have been shown to be able to find specifically good solutions that generalize well. But there's nothing about stochastic gradient descent that is in what you write down on paper when you describe a Bayesian neural network. So what we know actually is that there are many different parameter settings that fit your training data, and from that intuition, it might be the case that you are just very uncertain, and you might not be able to get the type of confidence that you would want for a practical applied decision-making problem. You don't actually have to interact with that huge level of uncertainty very much in practice because you're using approximations, and many of these approximations are built on one solution found through traditional methods of training neural networks. And it's possible this is obscuring potential problems within Bayesian neural networks. So we would really like a way to separate ourselves from approximation and from traditional training algorithms to figure out what does the Bayesian neural network written on paper with all of the parameters it has represent in terms of uncertainty. In order to do this, we do have to use some model that we can work with in terms of cost constraints in the real world. So we will make some simplifications. One thing we could consider is something like a random features model, where we only learn the last layer weights of the network. And this can be very useful for studying things like double descent. But we're very interested in cases where different parameter settings map to the same predictive function, as well as where different parameter settings perform the same on the training data, but differently elsewhere. And there's less of these cases if you consider a random features model. Further, we're really interested as well in whether this type of multimodal posterior distributions we find map to multimodal distributions in predictive space, and we won't see this with a random features model. So we want something that will tell us how our Bayesian neural network can distinguish between different interior parameter settings. This motivates us to propose this prior, where for the last layer weights W, we use a continuous prior and a fairly traditional choice of a Gaussian prior, just to understand the sort of implications of this common choice. But for the interior parameters, we'll group them all as theta for the moment, and we'll say that there's a finite number of candidates for what theta can be, and we're using a discrete prior on these. What this means is we can exactly write out the predictive distribution for this Bayesian neural network, and it's the sum of terms corresponding to each candidate theta j. This distribution, I'm not sure if you can see the highlighting very well, but it's in blue. For the new observation at each step is the predictive distribution for the corresponding random features model, and it's going to be Gaussian because of our assumptions. So we have a mixture of Gaussian distributions, and we can expand out the weight in this mixture corresponding to each candidate and find that it depends on the marginal likelihood of that candidate compared to the marginal likelihood of all other candidates in that set. This is going to give us some intuition on how to choose good candidates, and I'll come back to this in a second. We have a lot of advantages from this particular model. It's fairly flexible. We don't have to make assumptions on the behavior of the input data. We can represent different model sizes, different activation. We can enforce layer sparsity. We can also compare the behavior of this model to various popular approximations. Now the question is, how do we go about setting the candidates for this model? The first thing we tried was just inspired by the popular choice of Gaussian priors, And I'll go through this a bit quickly, but we basically draw these parameters from a Gaussian distribution. We find that when we look at the predictive distributions, they are fairly multimodal, but we also see some effects along the problem where we are predicting when the number of observations is close to the number of last layer parameters. We tend to find unimodal distributions, and we think this is because our prior doesn't allow certain covariances between the interior parameters. So what else can we do to find the good solutions? We can see that each mode will have maximum weight when the marginal likelihood of that candidate is large compared to all the others. And in fact, if we choose the optimal marginal likelihood, the weights corresponding to suboptimal candidates will decay very fast. So if we specifically have a set of optimal candidates, we can argue that we are representing what a Bayesian neural network with a much larger prior would find. It's a bit difficult to optimize this likelihood with respect to theta, but we can easily write down what the optimal covariance of the last layer weights is based on the covariance of the training data. And from there, we are able to demonstrate that for specifically a ReLU network, there are theta that map to this optimum training covariance or optimal covariance of the last layer features that's possible for a ReLU network to produce. From here, we can systematically sample candidates that are optimal for our problem. When we go back to looking at predictive distributions for one hidden layer, we find multiple modes, but they kind of blend together. If we start increasing the number of hidden layers, things get a little more interesting. We tend to see less predictive variance, but also some development of heavy tails. So at this point, we really want a more systematic idea of how what we're finding in parameter space maps to the function space. To start to get an idea, we freeze everything about our neural network except a specific hidden layer and start increasing the number of parameters in that hidden layer. For the first plot, that's the first hidden layer, and the second plot, that's the second hidden layer. First, we find very reasonably that more training data produces less variance in our predictive distributions. We also see kind of an interesting effect where the number of parameters, when the number of parameters in the layer is close to the number of observations, and you increase the number of parameters, the variance decreases. We start to see some increase as our network becomes more over-parameterized, what you might expect in the left. But at a certain point, the effect of adding more and more parameters to your model starts to level out. We can conjecture that this might be because of parameter symmetries, so the parameters you're adding are actually redundant and not adding expressivity to your network. This gives us some unintuitive results in terms of uncertainty representation. For example, when we look at this case where we're plotting predictive variance against overparameterization, we can find two networks with the same overparameterization level where the network with more training data is less certain about the predictive distribution. We can also find that you can train one network and add more and more parameters, but become more certain about your distribution. We also find that the predictive variance tends to saturate much larger than the noise level, and that predictive variance is extremely sensitive to your choice of prior. And that if you allow much larger variance in your prior, you're certainly going to get larger predictive variance. Because of this huge effect, and because a lot of our parameters seem to be redundant, you can wonder whether we should actually be putting a Bayesian prior on all of these parameters that's allowed to vary at all. Fortunately, there is a line of work that describes partially stochastic networks, which the first paper cited here will tell you exactly how to choose certain parameters in your neural network to give priors with non-zero variance in order to be able to train your network and theoretically be able to represent any type of distribution. We can implement these for the same size network as our Bayesian neural network, and what we first see is that the partially stochastic networks tend to perform much better in terms of generalization than the Bayesian neural networks. But what about calibration? Interestingly, if we look at calibration based on the quantiles of our predictive distributions, the partially stochastic network tends to be overconfident, but it is not super sensitive to the scale of the prior that we're using. By contrast, the Bayesian neural network has priors that you can find that produce very nice calibration results, but if you change the prior a bit, you can quickly end up with a predictive distribution that is too diffuse and underconfident. So where does this leave us? There are certainly formulations of Bayesian neural networks that can be confident and can be calibrated, but you are very sensitive to the specific choice of architecture you use and the specific choice of prior. So we really need to evaluate their uncertainty results in a very relative to parameterization setting. And what we intend to do going forward is really to query these specific parameter symmetries and identify equivalence sets within them. We're also going to extend our approach to further types of network architecture and fill in some of the theory showing just how close this method with discrete priors is to an approach with continuous priors. Thank you everyone for your attention. I'm very interested in whatever questions you have.
Questions for Kate? Please.
So what exactly is the connection between these symmetries you have in the parameterization, which obviously causes some trouble for uncertainty quantification, and this idea of partially stochastic networks? So do you try to completely get rid of these symmetries and only have one, let's say, target parameterization, or what is the idea roughly?
Yeah, so from my perspective, looking at the Bayesian neural networks, it really seems that when we move from posterior space to the space of the posterior predictive, where we're predicting functions, the existence of symmetries in posterior space is causing some collapse. So the intuition really is, like you said, I'm hoping that if I use these partially stochastic neural networks, this might actually be the more reasonable approach to uncertainty quantification, where you're only using the parameters you need. But it really does seem that maybe these two methods are estimating two different predictive distributions. So there's some work necessary to understand exactly what each one means.
Please.
Yeah, very stupid question, but in the charts where you show the calibration of partially stochastic and SDNs, is it possible to come up with a different prior for the partially stochastic neural networks that will also lead to calibrated uncertainty? Like, I mean, yeah, what is terminology? Yeah, the same if you were to fiddle with the prior.
Yeah, and in this case, I'd have to expand the prior out quite a bit. It's definitely worth checking, so I can't tell you for sure. My intuition is yes, but that the prior would then seem very unintuitive.
Okay, let's thank Kate again.